We now are going to turn our attention to a specific type of parametric equation known as a polar function. This is a type of equation that overlays on top of the rectangular coordinate system, except instead of us using a rectangular coordinate, that is x and y, where we go across x and up y, we're going to use a circular system based on concentric circles, where we go over a specific radius and then around a certain degree measurement. So taking a look at our picture below, we have a point that we're going to describe, and let me just emphasize the point for you so that you know where it is. We have this point here, x, y, which we obtain by going across x and up y. But an alternative for us is to go over a distance r and around some angle x in order for us to arrive at the point. It's the same point, just we're finding different ways of describing its location. So we are describing the location but using different methods of how to get there. We have a few measurements that we need to take. It's easy for us to understand x and y because we don't have to worry too much about anything else. But in terms of how we get to the point via our polar coordinate system, we're supposedly on a circle, and this circle has a specific radius that that is subtended. So we have to understand how to find that radius and then how to find our specific angle that we are upon. The first thing we're going to describe is our modulus. The modulus is the distance between the origin or the pole and the point. So it's the length of this line segment right here. And you can see from the picture that if this is a right angle, then it would make sense for us to use the Pythagorean theorem, that r is going to be related to x and y through the following, that r squared is going to equal the square root, or sorry, not the square root, but is going to equal x squared plus y squared, which implies that r can equal plus or minus the square root of x squared plus y squared. Now, while the modulus is described as the distance from the origin, or the pole, it is understood that this is a distance that could potentially be negative. So if r is less than 0, we travel along the negative x-axis. For us to reach the point. And if r is positive, of course, we're going to go upon the positive y-axis. Positive x-axis in order to get that distance. You're setting a distance from the origin, and then you're going to rotate around the origin once you've gotten the distance that you want to travel from it. The argument is the angle formed between the positive x-axis and the segment connecting the point and the pole or origin. So we're going to describe our argument as the angle that is made. That is the theta that is made between the positive x-axis, and we always measure it from the positive x-axis, and the ray. And we count the counterclockwise direction as increasing theta. So the counterclockwise direction is the direction we're going to rotate in for increasing theta. And so we can see, looking at our picture, that there is a relationship we can find between theta, x, and y. In particular, we know that the tangent of theta will equal the rise over the run, or y over x. And if you ended up with the tan of theta equaling something undefined, this would just simply imply that theta was either pi over 2 or 3 pi over 2, because along those axes, that is where the x values are going to be 0. The reason I'm not describing it in terms of the inverse tangent is because the inverse tangent has a restriction on the values of theta. And we understand that we have to solve this equation for theta and make sure theta is consistent with the quadrant of the point xy. Both of these, the modulus and the argument, these would be used if you are trying to convert between Cartesian or rectangular. So this is from going from Cartesian coordinates to rectangular. So these would be the conversion formulas in order to do that. If we're trying to go between polar and rectangular, we would use the next two. So these would be to convert between polar and Cartesian. So we assume we're given the polar coordinates and we want to find the Cartesian coordinates. We have the following if you look at the triangle. That is, if we want to find a way to relate x to r and to theta, we can see that the cosine of theta will equal x over r. And that is going to imply that, that x is equal to r, the cosine of theta. Secondly, we can see from the picture that the sine of theta is going to equal y over r, and that's going to imply that y is equal to r cosine of theta. So those would be our conversion formulas to go between the polars. If we have the polar coordinates, we can find the rectangular coordinates that match it. So let's make a quick comment about the uniqueness of these representations. Because of the circular nature of the polar graph, we can have several different polar descriptions of the same location, because you can either rotate clockwise or counterclockwise, which means that in some sense, if you look at a polar graph, let's take a look at a polar graph, and you wanted to plot a point, say this point right here, you could obtain getting to that point there by going around or going out a certain distance and then around in the counterclockwise direction. You could also go out on the negative axis and go to that point in the counterclockwise direction. You could go out on the positive x-axis and go in the clockwise direction this way, or you can go out on the negative x-axis and go around this way. All of those are going to describe precisely the same point. And so we have several different ways that can describe precisely the same location. Cartesian coordinates, however, have only one representation. So they are unique in the way we can write them.